Society, Student Branch Chapter, University of Dhaka, celebrating the 75th anniversary of transistor. We have with us our respected speaker, Dr. Saif Salahuddin sir, our chairman of our department, Dr. Anis sir, our respected faculty. So before going to the main topic of today's talk, let's take a brief look at our EDS chapter here at University of Dhaka. So the IEEE student branch started its journey in 2015, and we opened the EDS chapter here in 2021. So it is a great pleasure for us to note that we are the second ever EDS chapter in Bangladesh, and the latest addition to the family of IEEE student branch here in Dhaka University. So our motto is promoting excellence in learning and research in the field of electronic devices. The activities of IEEE here is very rich and vibrant, and we have some other chapters like IEEE Computer Society, IEEE Science Group, IEEE Robotics and Automation Society, and IEEE Women in Engineering. And we will be launching the IEEE Photonics Society here very soon. So currently we have 31 EDS student members here, and we have our executive committee who is committed to organizing and planning various events to make our chapter more interactive and interesting to the students. So in our very short journey, we have arranged some events so far. Our first ever event was on transistor, past, present, future, and EUV to the rescue. In our second event, Dr. Chauhan from IIT Kanpur discussed about modeling and simulation of negative capacitance transistor. At the beginning of 2021, we have arranged a comprehensive workshop on quantum computing in Bangla, targeting a wide range of audience to make it more accessible to them. We collaborated with Dr. Pramod Sinha from IBM to conduct this workshop. Next, we arranged an event on the exciting world of 2D materials, where Dr. Khandekar talked about its applications and future scopes. Then, in our last event, Dr. Ahsan from Intel talked about the history of IC research and some state-of-the-art technologies involved in this field. So our chapter is quite young in this journey, and recently we have been awarded a subsidy grant from IEEE Electron Device Society. We have been granted USD 1,000 to keep our activities and make it more reachable. So coming to the context of today's event, in 1947, William Shockley, John Bardeen, and Walter Brattain invented the transistor, and the world has never been the same after that. Here, 75 years later, today, the world has seen unimaginable progress due to this invention, and the transistor itself went through some thrilling journey and some unique development along its journey. So in our website, official website, we have highlighted the 3 generations of transistor. The details will be found in the website. We also update regularly about our activities, so I will request everyone to check it out and stay tuned for our next activities. So I will not take any longer. We are eagerly waiting for the main talk today. So now I will request Dr. Mainur Hossain sir to introduce our speaker to the audience. Thank you.
thank you, Aminul. So, welcome everyone to today's presentation. So, I'm very glad to introduce today's speaker. So, we have with us Professor 𝐶 𝐶. So, I'm just going to give a brief introduction of his career. So, Professor 𝐶 is currently a TSMC Distinguished Professor at the University of California in Berkeley, USA. He completed his bachelor's from 𝐓𝐻𝐡𝐞 in 2003 and his PhD in electrical and computer engineering from Purdue University in 2007. So, Professor 𝐶 is a fellow of IEEE and also a fellow of the American Physical Society, or APS. So, actually, his contribution to the field of electron devices is very vast, and it is actually very difficult to summarize it in a few minutes. But I'm going to actually just point out some highlights. So, Professor 𝐶 made very significant contribution, pioneering a field of negative capacitance, which is basically going to change the next generation of computer chips, enabling low power computation. So, Professor 𝐶 has won various awards, and he is the winner of the Presidential 𝐒𝐿𝐴 Award for Scientists and Engineers. And this is the highest honor bestowed by the US government and on 𝐒𝐿𝐴 scientists and engineers. So, this is a very big achievement. And obviously, he has published in very reputed journals, including Nature and Science. And his paper has been highlighted by the Applied Physics Letters journals as the most important paper for a given period of time. So, with no further delay, I would like to invite our speaker, Professor 𝐶, to give his talk. I think all of us are eagerly waiting. Thank you, sir.
Slide. Folder to file that.
माइक्रोफोन की लागत है कि पीछे से सुना जाए सुना जाए नाम अभी माइक्रोफोन यूज करते हैं. All right. So thank you very much. Thank you very much for giving me this opportunity to be here. I was just telling Mike that I have come to the outside of the building sometimes because my sister went to the chemistry department. When I was still in the school, I never came inside the buildings. But in these buildings, many of my family members, including my father, he graduated from the chemistry department as well. And so it's a fantastic opportunity for me to be here today. So what I'm going to talk about is negative capacitance. Is something very close to my heart. I came up with this concept when I was doing my PhD, and till now, that was almost 15 years ago, and till now I'm still working on it. So yeah, so let's see what this is. So just a few words about why we do what we do. When we think about computers, so just on a very broad sense, I work on computers. But when we think about computers, we think about like a computer, but computing is everywhere in our life, right? If you think about it, computing impacts everything from data crunching to healthcare, even fighting a pandemic. If you think about COVID, it came up with the with a vaccine within 10 months. Okay, that is a remarkable discovery of the modern world, and it's only possible because we have very powerful computers. So actually computing goes everywhere. Often we kind of forget about it, but that's one thing. In the US, they often talk about the fact that if for some reason the computing network goes down for a day, there will be a lot of people going hungry because the entire food distribution system will break. Okay, so again, food distribution, we don't think about computing, but what makes it work is computing. So we should keep that in mind. But there are some looming challenges for computing, and I'm trying to show that here. So if you look at the y-axis, what it is showing is world compute performance in zips, that is zeta instructions per second, right? 10 to the 23rd. So it is showing how it is projected to increase. We know the data up to this much, but the others are projected. Okay. What this shows is what is the amount of energy that will be needed. So again, we know the data up to 2020, but the rest is projected based on how much power we need for every instruction of computing. Okay? So you can see that if this continues to go up, then at some point it will cross over the world's total energy production, which is not sustainable, right? In fact, by that time, so this is 2032. By the time it is 2032, the computing power will be 1% of world's total energy production. Even that is not sustainable. You cannot give 1% of world's total energy for computing because there are many other things we need to do, right? So there is a sustainability problem. We are increasing the amount of computing we do. You are probably doing that without even thinking about it. You are always using a cell phone. When I went to Kuwait for my undergrad, I did not have a cell phone, right? And then I got a cell phone in my 4th year, where I could only make one call per day because it cost me 15 times, which was a big deal at that time, right? So, but you are doing it, you are using it all the time. You know, if you look at how many of you use Twitter? I mean, in Bangladesh, Facebook is very popular. Tweeting is popular also in the Western world. And there are some calculations which shows that big political leaders like the president or somebody else who is tweeting, right? Because they're tweeting, their tweets gets retweeted all the time. Right? It's like if you make a Facebook post and everybody is liking it, something like that. A presidential tweet can take the energy, the same amount of energy that an average American family needs over the entire year. Right? You are liking your Facebook post, but that takes energy because that information has to go. And when the information has to go, somebody is paying for the energy. Okay? In your lifetime, it is possible that you will no longer be charged for your bandwidth. You will be charged for how much energy you spend. Because energy is a problem. By now you know that already, because by the time I was here in the last 3 weeks, the government has said we don't have enough energy, we are going to do load shedding, right? But this energy for computing is catching up, which is a big deal. And so those of us who work on computing technology, we think about what can be done to reduce energy. And this is where my work goes into this material called ferroelectrics, and I'll say a few words about it. And we believe that ferroelectrics can fundamentally reduce the energy dissipation in the basic building blocks of computing. So the idea is, if you can reduce the energy dissipation in the basic building blocks, then the entire energy in the entire system will go down, because the basic building block is becoming more energy efficient. That's that. And I'll talk about why we think that way. So how many of you have heard about ferroelectric instruments? Not too many. So How many of you know about insulators?
All actually.
Everyone, right? So that glass is an insulator. Why?
Conducting.
Yes, sir.
There is no electron in the conduction type. There is no free electron.
There are no free electrons. Why is there no free electrons? Band gap is very high. Very high. Very good. So now, let's think about an insulator, which I'm trying to show here, where I'm showing the unit cell and all these other things are atoms. Okay? And let's think about it. There is a metal atom sitting in the middle, except that metal ion is slightly non-centric. So it is not in the middle of the cube, just a little bit displaced from the cube. What will that do?
Polarization.
It will give you a polarization, because if it is not in the middle, it means that in one direction it is giving you a positive charge. If there is a positive charge, then there is a negative charge. It means now you have a polarization. That is the material that gives you ferroelectricity. Materials which have that little bit of displacement. Okay? Now, if you look at the internal energy of that material, I'm showing it here, y-axis is energy. Energy, x-axis is polarization. Okay? It looks something like this, like a W. Okay? Why W? Because it has a polarization. That means when it has a polarization, it must have the lowest energy. So positive polarization, negative polarization must have a small energy. In the middle, it has a high energy. That's why you see a W like polarization. This is something when we try to measure it by applying a voltage, we see a hysteresis. Again, why hysteresis? Because negative polarization, positive polarization has the same energy. Okay? So there, where you are, whether you are here or there, depends on the history, depends on where you came from. Because it depends on the history, we see the hysteresis. Okay, so that's a ferroelectric material. It's an insulator with a breaking of the centrosymmetry. There is a breaking of the symmetry in the crystal. Okay. All right. So let's look at it a little bit more deeply. So I just showed one unit cell, right? But a material is not made of one unit cell, it has many unit cells. So let's think about it as many unit cells. And each unit cell, we just agreed that there is a polarization. If there is a polarization, what happens? There is an electric field. If you have charge, field lines come out. So that means that these many unit cells, this one, they all see each other because they are seeing an electric field coming out. Okay? Dipolar interaction. All of you must have seen this, right? This equation, P minus R cubed. You have seen this, and this dipolar interaction, you can basically say, hey, we have big computers now. I'll take a ferroelectric material. I know the coordinate of all the atoms. I put my polarization in all the atoms. I basically calculate this equation and sum over them. Okay? I get the effective field. So what I'm calculating here is that what is an effective field on one atom, because there are so many polarizations around. Okay? And if you just honestly put that equation in your computer today, you will get the correct answer. It's actually a very simple equation, and it converges very well in a computer because it goes as R cubed. So if you go a little bit away from where you are, the interaction goes down very fast. And as a result, this summation will work very fast. Okay? It will work very well, you will get a very good answer. As a result, these days, it is very difficult to tell my students to actually do the math because they can put it in the computer and see that. Okay? However, it turns out that in 1950, it's later, if you actually go into solid state physics, solid state devices or anything, you will always work with Slater's discoveries. He is the person who worked on electronic materials. So Slater actually figured out how to do this analytically, and he got an answer, which is which gives a very accurate answer. Okay? So if you look at this answer, it looks like is summation of these three terms. I highlighted these two because if any of you works on dielectrics, this is what you will find in textbooks. Okay, standard dielectrics gets these two terms. Okay, if you have not worked on it, don't care. Right? What the ferroelectricity brings is this third term. Okay, so that's just to distinguish between dielectrics and ferroelectrics. But the main point is, if you do that, you see that the first two terms is P over epsilon and P over 3 of epsilon. We can different sign. So these two will give you a negative sign. Right? Just two. It will give you a negative sign. But if I add a third one, the entire summation becomes positive, which means that the electric field will be positively correlated with polarization. This is very interesting thing. Why? Because it is saying that if I have a polarization, where did the polarization come from in the first place? There was a centrosymmetric bracket, right? There was a little bit of displacement of that. This is saying that if I have that polarization, electric field lines work in a way that it is positively correlated with the polarization, which means it tries to polarize the material even more. Right? So it is trying to distort that atom even more. But it keeps going, right? It polarizes even more. Electric field lines is positively correlated, so it tries to polarize even more strongly. And as a result, what will happen? If you take something and you keep distorting it, like this, at some point it will explode, right? Which is a fantastic thing, but unfortunately it does not happen. Right? In nature, you don't see something suddenly exploding. But something has to stop it. So if the electric field lines is trying to distort the lattice, something has to stop it. And you can imagine what that is. That's the spring force of the material. If I try to stretch it, it's something that stops me, right? That is your spring force. So that every material has that. And so the thing is, spring force is again very classical. Spring force is just ax squared plus bx to the power 4 and whatever, right? It's a very simple thing. If I ask you why this is x squared and not x, you should be able to answer that. It's spring force. The spring does not care if you stretch it in this way or that way. Plus x or minus x does not make any difference to it. So that means that if you are writing anything with x, it must be an even power of x. So that's why it goes as x to x squared and x to the power 4. Right? So I have now these two forces. One is the spring force, the other is the dipolar force. Okay? So these two forces act together, and when they act together, they give me this blue line. So I am adding the blue line with the orange line. I get this solid line. Right? So initially, the dipolar force is strong, and after that, the spring force is strong and it takes over. And as a result, what happens is I get these points where the net force is 0. Which means the material then will try to go to those places and be stable, because no material wants a net force on it, right? In equilibrium means every material has net force equals to 0. So the materials will go there, and you can immediately now see at that point the polarization or the distortion is non-zero. This is why a ferroelectric material goes through what we call spontaneous polarization, and it gets a permanent polarization. Right? Okay. So this is a very simple description of how ferroelectricity forms. But you see that this already tells us all the things that we need to know. What I have done here compared to here is that I just rotated the axis by 90 degrees. So those were these F=0 points. And potential energy, again, I think many of you have already taken electromagnetics. If you have electric field and if you have polarization, the energy goes as E dot dP. Very simple. So you take E dot dt on this card, you get this double looping energy landscape automatically. Okay, so now we know where this double looping energy landscape came from. Okay, But now that we know this, we have an atomistic theory as to why a ferroelectric material will give me this energy landscape and give me this hysteresis. At the same time, it tells me that right here, polarization is charged, electric field is equivalent to voltage. So depolarization over the voltage is less than 0, which means right here I have a region where the capacitance is negative. Okay. Similarly, if I compare that with the energy landscape here, right here, this is the region where capacitance is negative. Make sense? So far I have not said, okay, why am I even interested in this? We will talk about it. But negative capacitance by itself is interesting. So just because of something being interesting, right here I see negative capacitance. I also see that this thing is not achievable. Why? Because this region is not the minimum energy position for the material. So that if I just take a material, it will be here or there. And there it is not negative capacitance. It has a region where it has negative capacitance, but it is not there by itself. So I have to do something to achieve it. Okay? So that's what we will see. What can we do? Okay? What we do is that, let's say this is my energy landscape of the ferroelectric material. What I'm doing is I'm just adding another dielectric to it. What is the energy of a capacitor? Q square 𝐶, right? It's written in the slides. Nothing to think about. Alright, that's a parabola, right? So that's a parabola. And here you see this double parabola. So if I create that series network of two capacitors, you are all electrical engineers, right? So I'm pretty sure you know all about series capacitors. So if I put this two, energy landscape wise, I am adding this W with a parabola. And if the summation is good, is appropriate, then I will get this green plot because I'm adding orange with the blue, and when I add those two, I can get this green curve. And you can see that for the green curve, the minimum energy position is here, which means to minimize the energy of the composite system, of the total system, the material wants to be here, where locally the ferroelectric is in the negative capacity. Okay? So ferroelectric by itself, I cannot put it in a negative capacity. It's not thermodynamically possible. But I have figured out a way to put it there. Okay? Alright, so if I can put it there, what do I see? You see that if I look at the green curve, remember that the y-axis is energy, x-axis is Q, charge. So compare the green curve with the orange curve. I am getting the same charge, same amount of charge, but I need less energy compared to the orange curve. Right? So again, you are writing the equation for a parabola because it looks like a capacitor from outside. If I get same charge but less energy, what does that mean? The overall capacitance must have gone up, right? But the textbook told us that if you put two capacitors in series, the total capacitance must go down. Okay, so that means that if I want to test this hypothesis, this is what I need to test. So far, I'm only talking in the air. I don't all here. There's no real data experiments. But if I want to do an experiment, this is the smoking gun experiment. Because if I put two capacitors in series and the capacitance goes up, that tells us that what textbook told us is not correct. Okay? And that tells us that we have something new. That is the negative capacitance. Okay. So now one slide is to why are we even trying to do this? What is the reason? Right? When I write my funding proposals, I have to explain that why am I trying to do this. If I just say, oh, negative capacitance is very interesting, then say, okay, go burn. Right? So the point is, if I get less charge, same charge and less energy, I can get the same current at a smaller voltage. Because what is voltage? What is current? charge times velocity. If I can get the same charge at less energy, that means I'm getting the same current, smaller voltage, which means that I can reduce the supply voltage in all transistors, okay, without having to give up the current. And the transistors are the basic building blocks of all computing devices, so I can reduce dissipation, energy dissipation, energy requirement in all computing devices. That's the basic information. Okay. The great thing is, in a transistor, it turns out this series network that I needed, series network of two capacitors, is present by design. A transistor has this semiconductor channel which has its own capacitance, and it uses a dielectric as a gate. If I can replace the dielectric with a ferroelectric, it automatically reduces that series connection. I am really simplifying it here because you have to have material compatibility. I'll talk about that. But conceptually, this is it. That's how we can get. Okay. So let's talk about some experiments now. So as I said, negative capacitance means that I put two capacitors in series, I get an enhancement in the capacitance, right? This, interestingly, if you just use your known formula of two series capacitors, but take one of the capacitors as being negative, you get that from there as well. Very simple. Alright. So we have been doing these experiments for a long time. Our first experiments came out in 2011. And good thing is, after we did that, many other groups around the world actually reproduced the same capacitance enhancement in many different material systems. So that was quite satisfactory for us. So what I'm going to talk about today is an experiment which is relatively new. This paper is from 2019. Okay. So what we did is we created this series network, but it's a little bit complicated series network where we have multiple series capacitors. So PTO is lead titanate and STO is strontium titanate. STO is a dielectric, PTO is a ferrite, and we put multiple of them together. And I can talk about why we did that. But in the end, it's a ferroelectric and dielectric series. Capacitors connected in series. Okay. And these are actual experimental data. So this is something in literature is called superlattice, when we actually put multiple figures like this together. And you can see that the superlattice gives you this very large capacitance. Okay. So the fact that capacitance goes up, we can experimentally see it already. So from this experiment, we can say, oh, there must be something internally that has a negative capacitance. But the reason I chose this experiment, is we can do better. We can actually image this material. So what you are seeing here are actually individual atoms. Okay? So we do what is called transmission electron microscopy. And this is not something that you can do in any transmission electron microscopy microscope. This needed one of the world's best TEM, which is fortunately there at Lawrence Berkeley National Lab, which is just up the hill from me. Okay, so it has one of the highest resolution. So what you see are actually all the atoms themselves of the material. So once we can see the atoms of the material, we can see how much the atoms are shifted from the center of the tube. When we see that, that gives us the polarization. So these polarization vectors, you can see the atoms, right? These polarization vectors are drawn by looking at how much the atoms are displaced. So I know the polarization. Okay. Now, can I know the electric field inside? If there is a polarization, as we discussed, there is an electric field. How many of you have already looked at PN junctions? Everyone? Does PN junction have a built-in field? Can we measure it? Yes? How?
the barrier voltage. No, not measure, but we have to.
It's a calculation. How can we measure voltage? Can I put a voltmeter across a PN junction and measure through? No. You cannot measure the internal electric fields because it does not shift the far minerals. Okay. So there is a way to measure the electric field. How? So let's say I have electric field inside my material. Okay. Let's say I put an electron beam on it. What will happen? The beam will deflect. So if you have a very good detector on the other side, by looking at the beam deflection, you can figure out. So exactly, our textbooks, most textbooks are written 30 years ago. We do not do that at that time. So they will say we cannot measure the internal electric field. Actually, do everything by using these electron beams. Okay, not by using a voltmeter, but using the electron beam. So we do that, and we can figure out. This is difficult to see, I guess, maybe. These are the electric fields that we can measure inside the material. Okay, so we have polarization map. We have electric field map. So again, if you have taken electromagnetics, once you have polarization and electric field, you know everything about the material. Because displacement is epsilon E plus P. There is nothing else. And this epsilon is just E, free space epsilon. So this is a fundamental constant. So I know E, I know P, I know D. So now I know everything about the material. So what I'm showing is I took a line cut along this line, and I'm showing you along that line I get this polarization and this electric field. Okay? So once we know that, we can actually figure out the internal energy, which is E dot dE. And so we figured it out, and you can now see that locally I am seeing this inverted parabolas. Okay? This is, you see that the material is sitting in regions where the energy is larger than the ground state energy. Okay? Compare that to this thing. This is what I try to describe, that locally ferroelectric will be stabilized at a higher energy position compared to this ground state energy. So this is something we can actually atomistically image and see. Not only that we can measure the capacitance has gone up, we can atomistically see how it has gone up. Okay? So that makes it a very self-consistent measurement. And so this was to some extent the best of our fundamental experiments. We have done many experiments, but I wanted to highlight this one because this is where we can actually atomistically see that it will capacitance. Okay? So up to now, what we have talked about is all just fundamentals, right? All fundamental physics of the capacitance. Now we should talk about if it can be used, right, for anything to solve. So it took us a long time. You see that I talked about the first negative capacitance paper we wrote in 2008, and the atomistic imaging came in 2019, so 10 years. Okay. So now, just on the fundamentals. Now, when we think about real applications, I explained that we want to put it on a transistor and reduce the voltage, right? So when we try to do that, it turns out there are challenges which are almost fundamental and very difficult to overcome. So first of all, these are FinFETs. I just saw this picture like in your EDS chapter's website, right? You just showed it. Okay. So these FinFETs, what is the latest node today? Does anybody know? So Intel, like a month ago at VLSI Symposium, they showed 4 nanometers. 4 nanometers. 4 nanometers does not mean the channel length is 4 nanometers. I hope all of you know that. 4 nanometer has nothing to do with anything that is 4 nanometers. Nothing in the transistor is actually 4 nanometers. Okay? It's just a name. But the point is, for the 4 nanometer node, the gap between the fins is 29 nanometers. Okay? So think about it. You have a fin. A FinFET looks like this, right? This is the fin. So there are two of them, 29 nanometer apart. So you have to put a gate oxide, like this. On top you have to put a metal, put like this. So when you are putting things like this, it forms on this side wall, and it forms on my hand as well. So if you put 5 nanometer of metal, then it is 5 nanometer here, 5 nanometer here, you have already taken 10 nanometers of the 29. If your gate oxide is 2 nanometers, you have already taken 4 nanometers. So you have now taken 14 nanometer of the 29 nanometer. So you are putting all of this, but you have to put a metal connector, right? If you make a metal which is 10 nanometer thick, the metal does not remain a good metal. It's a big problem. So when we started working on the ferroelectrics, people said, yeah, you are doing very good fundamental work, but it's absolutely useless. Why? Because for conventional ferroelectrics, it is known that when this is thickness in angstroms, it is 1/10 of a nanometer. By the time you are below 10 nanometers, ferroelectricity goes up. So they said, I don't have the space for a 10 nanometer ferroelectric inside my fins. There's no space. So you are doing great physics, but I cannot use it. Okay? And the point is, yeah, I mean, I cannot use it. The conventional ferroelectrics are not usable. Okay? The point is that, fortunately, around 2007, a group in Germany discovered that hafnium dioxide, which is what we use today in our transistors, if you dope it and anneal it properly, it becomes ferroelectric. So we started looking at that because it's a very good ferroelectric material, and we thought maybe it will give us a better performance. So just as a benchmark, you should know that today's transistors use a gate oxide which is just 1.8 nanometer. Just 80 times 20 is 3 unit cells. So we started working on this hafnium dioxide based materials, and actually we got lucky. We found that these materials are really very different, and even at a 1 nanometer thickness, the material can be made with ferroelectric. Okay, so this is a very new result, just 2 years old, where we were able to see ferroelectricity is very, very thin. Okay. Fundamentally, we found that it is very interesting because conventional ferroelectricity shows that the distortion between polarization goes away with lower thickness, whereas for this kind of new ferroelectric, the distortion actually goes up as we reduce the thickness, so the material becomes even stronger than increase thickness. Okay. So again, very interesting from that point. But coming back to our application side, we know from our work on perovskites, this kind of material, superlattice, what we need to get very strong negative capacitance, right? And we have now this new type of material that we can stabilize in a very small thickness with ferroelectric. So we can learn from this superlatticing, and we can try to emulate that in this very thick ferroelectric. So what I'm showing here is exactly what will be used in today's MOSFETs, where I have silicon, a little bit of silicon dioxide, and then 18 angstrom, 1.8 nanometer of high K dielectric, which in our case, we are making a super lattice with our ferroelectric, exactly that 1.8 nanometer. Okay? And we immediately see the performance boost. So what I'm showing here, this is capacitance versus voltage of a transistor. The orange curve is our devices that we make at Berkeley. The blue curve is a 22 FDX. I think Michael knows a lot about those. We work for global foundries. This is one of the most advanced transistors, commercial transistors that we can use. And you can see that my capacitance is much larger than a very advanced transistor that is out there. If you look at the leakage currents look almost the same. That's because I have not changed anything in terms of the thickness. All thicknesses SI look like they are the same, but I'm getting much more capacitance, which means I'm getting much more charge. and a smaller pole. So that's the promise of negative capacitance. So if you now look at benchmarks, these red curves, red data points are industrial benchmarks. X-axis says EOT, that is the effective oxide thickness. What industry does is, if they want to go down in the effective oxide thickness, in other words, to increase the capacitance, they try to reduce the SiO2 thickness. So when they do that, the leakage current goes up significantly. So you can see that trend here. But what you can see that for every point, our gate stack gives lower leakage current at the same capacitance level. So these blue points are our gate stacks. Okay? And again, this is not just one versus the other. This is industrial benchmark. So we can actually do better than what industry has. Now, when you try to take SiO2 out of silicon, silicon does not like it. As a result, the mobility in the silicon goes down. So similarly, if you look at, you are reducing your T, meaning capacitance is going up, mobility tanks. This is industrial benchmark. We don't do any SiO2, it's called scavenging. We don't do that. As a result, our mobility is not affected. So our mobility remains there. So we can see that we can get capacitance enhancement, and we do not have to change the mobility. Okay, and that shows up in our transconductance. How many of you have heard about transconductance? It's okay if you have not. Transistor means that you are transferring resistance from input to output. If rather than a resistance, I talk about 1 over resistance, that is just conductance, that is transconductance. Okay. Now, if you look at the equations, transconductance becomes capacitance times velocity. So as a result, device technologies really like transconductance because it gives you the product of those two. So if by any means you increase the capacitance but your velocity has gone down, the transconductance will not change. So you will not be able to win. That's the point. So transconductance, because of that, is a very important metric. And right now, these are our gate stack transconductance, negative capacitance transconductance. We have the record transconductance for any 90 nanometer technology. For us at the university, it is very difficult to go down and make, let's say, 15 nanometer transistors. We are trying to do that. But this paper is really just from last December. But at 90 nanometer, we have the world's best transistors right now in the university itself. So we are quite excited about that. So one of the other things about devices is reliability. I cannot just give you a good device and say, okay, go use it, but the device, stops working after half an hour of use. Then you will get very angry, right? So as a result, what people do is they try to measure the reliability of transistors, and the reliability depends heavily on the grade of silicon. So from when the industry went from silicon dioxide to hafnium dioxide, this was the biggest question: will the reliability be satisfied with a new gate oxide? So anytime we talk about a new gate oxide, like negative capacitance gate oxide, we have to do measurements. So that's what we do. And again, long story short, compared to hafnium dioxide, we actually see better reliability at all voltages and all temperatures. So again, this is also a very new result. This is from 1 month ago that we presented and realized the program. Okay. So we are, I'm showing you results which are almost cooking right now, because we were able to start building our devices with the gate stacks and all of those only very recently. But we are starting to see better results than the most advanced technologies. All right. So again, just a summary of the industrial benchmarks. I already showed you this curve that in terms of leakage, we get the same capacitance but at a lower leakage. If you hold on the leakage, we can reduce the DOT, which means we can increase the capacitance. So you say that I want this much leakage from industrial benchmark, I can reduce the EOT by this much between these capacitors. If you look at the mobility, I can hold on to the mobility. If you look at the reliability, I see an exact opposite trend. These opposite trends are possible because we have a negative capacitance, not a positive capacitance. Okay, so yeah, so interesting area. Now, one thing you can ask that, okay, you have shown me 1 nanometer of ferroelectric. The question is, how thick can we go in this way, right? So very recently, again, this paper came out probably 2 months ago. We showed that zirconium oxide, which is just a simple binary oxide without any doping, we can make it ferroelectric at half a nanometer. Yeah, just half a nanometer. Half a nanometer is just 1 unit cell. You cannot go below that. That's it. That's the limit. So what this shows is that yes, we are able to get ferroelectricity at the limit. So scaling wise, it's not a scaling problem. Okay. So I am almost at the end. I just wanted to summarize that we started many years ago with the physics theory, but we started doing experiments on fundamental materials, but we learned a lot from there. And we were able to translate those learnings into materials that we can actually build on transistors. And with that, we are starting to now see results that has given us record performance compared to even the most advanced transistors. But one good thing about the physical concept is that, you know, people figure out many other ways of using it because, you know, I went after negative capacitance transistors, but there are many others who have been using negative capacitance for other things. So, for example, negative capacitance has been used for supercapacitors now for energy storage. This is something that I'm very proud of. People are using it for battery as well. I'm proud of this work is because how many of you know who this guy is? John Goodenough.
Nobel laureate.
Nobel laureate for lithium-ion batteries. So he won the Nobel Prize for inventing lithium-ion batteries. But even his group is working on our concept to actually improve battery performance. So that was a big, satisfying thing for me. But the point is, if you actually look into literature, people are figuring out many other ways of using the concept, which is what happens if you are able to establish that. So all right, so let me end there. So basically, you know, we have been working on negative capacitance for some time on a physical concept. We think that the phenomenon is established, very robust grounding now. The main question was, until 3-4 years ago, was the ferroelectricity in materials that we can put on transistors. But now we have these very thin ferroelectric materials, even down to 1 millisievert, right? And that I think is going to lead this technology into integrated ferroelectric devices, because we now see that we have materials that we can put on advanced silicon transistors, and we can actually do better than advanced silicon transistors. So on that point,
thank you, Professor Sai. So the floor is now open for questions.
With your perspective of energy storage, that is very, very important thing, right? What do you think of the commercialization and demand of down billions of dollars at least, not millions?
That's difficult to say, but I think, you know, energy storage wise, right now there is nothing that can beat chemical energy storage. So it is the conventional method. But
Apart from that,
right, so but supercapacitors are starting to be used I mean, there are some really, you can call mavericks who are trying to build supercapacitor-based batteries even for cars. But as intermediate application, there are lots of applications. The attraction rate is supercapacitor gets charged in a microsecond compared to like battery which take many hours. So for supercapacitors, I see negative capacitors may have a lot of because it is enhancing the capacitance. So the idea there is that in a capacitor you store the charge in the plates, but when the material has a polarization, you are storing some charge in the volume as well. So for the same footprint, the storage goes up. And I think there is a lot of promise there. We have been looking at some solutions where you want to put a supercapacitor integrated with the chip so that your entire standard can be actually kept in the standby mode. The energy that you need will be supplied by the supercapacitor. So I can see that there's a lot of application there. But yeah. Difficult to put a dollar on it. But yeah, energy storage is a big thing.
So, I don't know. You showed that the thickness of that layer is around 1 nanometer right now. So, what is the growth technique limitation about doing that much thickness? Because I know there is some limitation while going the silicon dioxide. You can't follow the real groove model. So in that case, you have to be about limiting size of that thickness.
So right now, 1 unit cell is the limit. We can go, this one, this is on this is going on, but this is going on, this is done with just 1 unit cell.
So the growth technique is emulsivity or
emulsivity is too fast. You have to do it. And the SiO2 part is done in a self-limiting process. So therefore, SiO2 we don't have to worry. It goes through that 8 angstrom thickness and it stops. After that, knowing that 𝐒𝐿 is in.
So after transistors, what are you hoping to work on next using negative capacitance and ferroelectric? You personally hoping to work on?
I'm going to work on transistors for a long time, and then I'm going to retire. Because there's a lot of work to be done on transistors itself. We definitely work on ferroelectric memory, and I did not talk about that here. But transistor is a big challenge. It has all kinds of material compatibility, so we are working on those. And I think that as we go from, let's say, FinFETs to nanosheet transistors, I think that the space that we can give will be even lower. So 1.8 nanometers today will have to go down to something like 1 nanometer. And then we have to redo all of these things. So I am hoping it will keep me busy for several years.
So you said that you are working to reduce the computational energy for the computers.
Reduce what? Sorry.
You are working to use the negative capacitance to reduce the computational energy. So what is the number that you have in your mind? That number you're trying to reach to the energy reduction rate?
So right now it's 10x lower compared to what we have today. That's my personal target. If you want a number, today's transistors are femtojoule per bit. That's the average energy expression. If you just take one transistor, it's much more than it's like amplitude per bit or something, 10, 12. But if you look at a full compute chip, it brings in all kinds of line capacitance, this and that. So you take an average, it comes out around 1 femtojoule per bit. So you can say from that point of view, 10 out of 2.3, 100 out of 2.3 is my personal target in the short run. Yeah. So what that amounts to actually is to run a transistor at 350 million. Today, transistors are running around 1 volt. But if you can reduce the voltage by 3x, then your dissipation goes by V square, which is 9 times.
Sir, you have said that hafnium oxide actually giving us better ferroelectric properties. So finally, at that last slide, you have said that zirconium, you are using zirconium. So my question is zirconium is better than hafnium oxide in all of the benchmarks like reliability?
So first of all, I want to emphasize that the hafnium dioxide that we are using is not a conventional hafnium dioxide, it's a ferroelectric. The second thing is, we are not at the stage to make the statement that zirconium is better than hafnium. I'm just saying that right now we have results of with just one unique cell of zirconium oxide, which is a ferroelectric. So you have to take that as a proof of existence, because what I'm showing here, even last year it did not exist. People could not believe if you went and said that I can make a one unique cell ferroelectric. Because fundamentally, ferroelectricity, we just celebrated the centennial, it's 100 years of ferroelectricity 2 years ago. Okay? And so many people are working on ferroelectrics, and the idea is you cannot reduce the thickness below 10 nanometers. So these results are very new, we are still learning, so we are not at the stage to say one is better than another.
Sir, I have several questions.
Go ahead.
So, first of all, what is the switching performance of such kind of transistor?
What does that mean?
Like how fast it can go from on to off stage?
So, you see, this is, I did not spend too much time, but you can see this particular data is up to 20 gigahertz. We have other results, if you look at this paper, up to 40 gigahertz. So you can say that up to 2.5 picoseconds, it looks fine. Fundamentally, one can say that the switching speed is essentially the same as hafnium dioxide, because switching speed depends on the force that you are applying on an material. And force is Q times E, right? Electric field. And if you have a sheet of charge, what is the electric field? Charge divided by the permittivity of that. So, in a transistor, whether you have used a high K hafnium dioxide or ferroelectric K hafnium dioxide, the inversion channel charge you have is the same, because that belongs to silicon. So if you have the same charge, you have the same electric field. If you have the same electric field, you can apply the same force on the atom. The atom is the same, which is hafnium dioxide. So therefore, there is no reason for the dynamics to be different.
So at lower energy we can get the same kind of switching speed, right?
Yeah, right. So that's the point about reaching the same current at a smaller voltage. You need same current to make sure that you run at the same speed.
Thanks. So I had another question, like here you use hafnium dioxide. Like what's the availability of such kind of materials for greater scaling? Like silicon dioxide is everywhere found, but what are the scopes of such materials?
Hafnium dioxide is actually quite available. The biggest thing is you are using an extremely low amount of hafnium, because you are using 1.8 nanometers. Very little. So even if you are using, millions of wafers, 1.8 nanometers still amounts to that. Silicon is, the importance of silicon is because your handle is silicon. That thing is thick. So if that was expensive, then we'll do it. Which is the trouble for, let's say, gallium nitride. Gallium is very expensive, so you cannot have that handle.
Any other questions?
I have a question. You have shown that you have calculated capacitance T14 𝐻, the same
Measure.
So now, let's say I'm designing some sensor or something where I want to enhance the surface rate, or maybe I want to make a reflector to increase the reflectance, something like that. So can I use your negative capacitance material as a nanosheet or something? And can I tune the voltage to vary the capacitance to change the property? Like, can I use such material for like this kind of devices?
So the point is that voltage tunability of the capacitance is simply this. Like applying voltage.
But that would change the operating frequency, no?
This won't change the frequency, it's just a capacitance.
Okay, but the previous graph you showed, like the last slide,
You mean this one?
yes, where you have different
So this
VT
is,
levels.
so what I'm showing here is capacitance is a function of frequency,
Right.
which is a flat line. So it is just to show that there is no distortion. And it is changing as a function of voltage.
Right.
So it is a different statement of this plot. Here I don't show you the frequency. But if I show you frequency, all of them will be sitting on the same line. But think about, now I'm plotting it with frequency, but I'm plotting just this point as a function of frequency, and this point.
Yes.
So that's what I'm showing here, where you can see that capacitance changes as a function of voltage, but is reasonably flat.
In your operating range, it's reasonably flat. So the epsilon will be flat as well?
Yeah, so that's what it is. Yeah, with frequency it's flat, with voltage it is changing.
Yes, I understand. For quite a big range of frequencies, epsilon and C are flat.
Yes, there is no distortion. So that's
Right.
the essence.
Okay.
Any other questions?
So we have recently faced crisis on chip shortages. If you make this device and it comes to market, how hard you will need to produce this, and we will be able to work on this.
It will have zero influence on chip shortage. Chip shortage is coming because of the fact that supply line, if you look at how the computers are made, there is this supply industries that are required, which are all over the world. So, for example, my group recently designed a chip. The chip was built last year, in the middle of last year, okay? From global markets, what my group is that. We got the chips, but the chip has to be put onto a board so that we can measure, right? And the board is made in Hong Kong. And we have been waiting for a year for the board to come to us so that we can place the chip so that we can measure. So similarly, when they are building this iPad has many components, and if you look at it, these components are coming from many different parts of the world, and the supply chain is getting affected mostly because of COVID. The Hong Kong closure has happened because they said the COVID is increasing and they are going to shut down all their industries, so they shut it down. So once they shut it down, the orders pile up, right? And that creates a shortage. Then somebody who is doing the packaging, they are probably shut down. When they are shut down, the orders. So, yeah, chip shortage is a very different scenario. And until the pandemic is over, I think it is going to be different. Oh, the pandemic, meaning the COVID pandemic is over. At least COVID pandemic. I mean, of course, recently now war is another concern. At least until the pandemic is over.
research stage to commercial and widely available stage?
It's already going into industrial R&D. Industrial, big industries already have our data stack. So after that, it's outside our hands.
You're part of this number, mind making. Are you?
Sorry?
Are you part of the mind making number? I mean, it's partner of the device.
No, if the industry is commercialized, I make no money. Yeah, I'm an academic.
The many academicians, they are venture capital.
Then you will start your own company. Meaning, you can start a company and if you're starting, if let's say semiconductor industry is like Intel, TSMC, they pick up the invention. So, freelance, for example, came out of Berkeley. Freelance, my colleague 𝐏𝐶 is credited for inventing. But I think Intel bought the patent for maybe few tens of thousands of dollars. So it's nothing. Yeah, that's because you cannot invent something and make a lot of money out of it, at least in our industry, because going up to a product takes a lot of hard work. So unless you do it yourself, nobody wants to give you the money. The minor does it, that he gets some money. And he pays a little bit of money for that.
And making a semiconductor fab is super expensive.
A lot of things like a transistor process probably have like 1,500 steps that has to go right. And so one invention does not make it one. I mean, DRAM, for example, Bob Dennard invented DRAM. We are using, everybody in the world uses DRAM. Bob Dennard made drone.
So why hafnium dioxide? What are the properties that we require for such applications in a dielectric?
Yeah, so hafnium dioxide, the attraction in there was that hafnium dioxide was already being used in transistors. So in semiconductor fabs, they are so sensitive that if you want to introduce a new material, they get very nervous. They don't want to introduce new materials. So hafnium dioxide, with hafnium dioxide is looking what they already have it. So that sensitivity was not.
Actually, I just to know the properties in the previous slide. I think can we use this property as voltage control capacitance? Get voltage control capacitance.
Yes, so it's a very typical transistor capacitance, and yes, the way we use transistor as a voltage capacitance.
I guess we are probably towards the end of the session. Any last question?
Sir.
Let's take one more.
I had one generalized question, if you permit. Like, what are your advice for third year, fourth year master's student who aspire for higher studies, specifically, let's say USP? What will be your advice?
Yeah, if they want to go to Berkeley.
I think the only advice is based on what I have seen from students is that one difference with, let's say, students from US and other international students like China, Taiwan, India, is that students from those countries often, I would say most of the time, that we see at Berkeley, they have a reasonable conviction about what they want to do. Because there are so many things you can do. If you look around, there are many things that you like. Maybe you like electromagnetics. Maybe you want to work on communication. Maybe you like signal processing. students, top students that we see often have given it a thought, and they have decided that I want to do this. And they have considered the pros and cons. So their conviction is very pure. When they come, their conviction, they have a purity of their conviction. Often students from Bangladesh, they don't have that conviction. They are thinking what is going on in Bangladesh. I have often found Bangladeshi students are often, how should I put it? They are embarrassed to think about money. Okay, meaning, let's say they are looking at 4 different things, and they think that studying this will give me the most amount of money. Okay? They are very embarrassed to accept it. And to me, especially in the US, nobody takes that back. If you want to make a lot of money, that's fine. That's okay. So, but I'm just saying that I find that Bangladeshi students often get very confused about what they would like to do. Maybe they would like to study something, but somebody told them, if you study this, you may not get a job. So then they're thinking, oh, then I will not make a lot of money. And but somebody told them something else. So that's the thing, that when I went for higher studies, I could see that it was a big problem for us because we hardly do anything. But today, all the information are available. So you could make a decision for yourself, like that. Yeah, maybe what I want to do is to make a lot of money. Then you choose what today tells you that will give you the most money. Or you say, no, I really like the physics of that, and maybe it won't give me a lot of money. Then you say, okay, I accept that I may not get a lot of money, but I will some. But whatever you do, I think that I find that compared to students from other countries, there is this difference in purity of conviction. And I think that, at least for good students, I find that they are today from the WD, they're going to all big schools, all the top schools. I think same will happen for this department as well. I don't see why it won't happen. It will happen. But so I think that going to top schools is no longer a big deal. You can get it. But I think what restrains our students from doing very well is that they often don't have that purity of conviction. This is what that's
Thank you, sir. Sir, for this further clarity, like how can one show such determination, like at the very beginning of their application? If how can one convince someone that yeah, I'm determined to do something?
I mean, look, you are all adults, right? My answer is, how can you say that this girl or this guy is going to be my soulmate for my entire life? You can never say that. I mean, you never know that answer, right? Basically you have a gut feeling. Based on what you know at that point, that's a true answer, right? And I'm pretty sure that if you ask yourself, there is something that you actually like. That does not mean 5 years from now you are going to like it. Maybe something else. But today, if you ask yourself, you will find an answer. And to me, that's what you want, right? I mean, that's if you give the highest priority on what you want, then that's what you want. I mean, that's the same thing I tell my students there. My undergrads, when they ask me that, what I want, whatever. You only can decide based on what you know today.
Okay, so I think we already ran past an hour. So let's thank the speaker one more time. Thank you very much. And I'd like to request our chairman sir to present him with the
Good, great.